In this lecture, we're going to look at higher order derivatives. And again, we'll define that as we go. I just want to review here. A function is said to be differentiable at a point, so point differentiable at a point. Again, if I specify x equals a is a fixed but arbitrary point. The fact that it's a function means by definition there's an associated y value, an xy ordered pair. That's defined because there's a function. So if this limit of the slope of the secant slope function exists, it equals a number. That number is, by definition, the slope of the tangent line, and we denote it as dy dx, change in y over change in x at that point. Okay? And again, the secant slope function is not defined when x equals a. If this limit exists, a function is said to be differentiable at the point. If it's differentiable at all points in an interval, right? This limit exists at all points in the interval, i.e. the slope of the tangent line exists, so there's a tangent line or linear approximation. For every point associated with the x value in this interval, the function is said to be d1. This function is an element of the set. D1 means differentiable first derivative functions on the interval alpha to beta. Okay, in terms of the notation, we defined an operator then. So a function f goes in, a function fx comes out. Well, it's a function. A function that works on functions is called an operator. We talked about this, and we denote this one by ddx. Right? We take the notation, we explain this from the slope of the tangent line over here. So again, the function fx gives us the slope of the tangent line when we evaluate it at a specific value, x equals a. And so this is why we chose this notation. So the operator is ddx, the differential operator. The function f goes in, or the operator acts on f, and the resultant, what comes out, is a new function, which we denote by fx. And again, the notation just comes from this slide, and we talked about it previously. Okay, so function goes in, a function comes out. This function fx is derived from the function f via the differential operator. And here's the picture. I just took this from before. If I specify a value of a, say, is 3 halves, right? X equals 3 halves, so a is 3 halves. I get a slope of that function. So notice from the function here, I get the point, right? By definition, the fact it's a function. So when I say a is 3 halves, I get a function, I get an xy pair, I get a point. And the derivative function, fx, gives me the slope of that tangent line. So the combination of the function and the derivative lets me construct a linear approximation at every single point along the graph of f. Right? And you can see from the picture where we're heading with this, right? We're going to wind up replacing the function by linear approximations, right? So that's what we have. So the function fx provides valuable information, the slope of the tangent line, about the function f. Right? That's what we have. Okay, well that's good. So at one level, that's a constructed point. At another level, function f goes in, function fx comes out. I mean, that's fine. And again, here's this relationship. When I write d dx x cubed equals 3x squared, I am saying that the function that's going in, the function f, is x cubed. Right, here's it in the picture here. And the function that's coming out, fx, is 3x squared. That's what this notation means. And the link between these functions is this operator ddx, right? So the function f goes in, the function fx comes out. Again, instead of saying f of x equals x squared, the number 2 goes in, the number 4 comes out. Here, the function x cubed goes in, and a function 3x squared comes out. And that function is called an operator, ddx. Okay? But we can look at this function fx as a function. It is a function. So just to be less distracting, I'm just going to call it the function g. Right? So let's just, g is going to be the function fx. It's just the rule. So we'll take g in this particular case to be 3x squared. And we can take its derivative. And you can go through the point definition just as we did before and come up with a slope of the tangent line at every point, right? Just literally applies at the definition, the secant slope function. again, it's not defined in A. We can come up with the extension to evaluate the limits. I'm going quick through here because it's just routine. I just really just cut and paste the slides from before. So my point is, for this function g, which we derived from the function f, I can come up with the slope of the tangent line at every single point along the curve, the graph of g. And this is that picture. So again, if I take a value of x equals 3/2, a is 3/2, 1.5, I get a slope of the tangent line to the function g. Now again, why you want to do this? We'll talk about this subsequently, but let's just say you can. It'll have use or we wouldn't be doing it. So you can do that. I get a slope of the tangent line. Again, I can wind up replacing the function g in a sense, if you like, with the linear approximations. So this relationship, the point and its slope, defines a new function, h. So this new function, so again, I get the point, the xy pair from the graph of g, because definition g is a function, whereas this function h derived from g gives me the slope of its tangent line. But it's just a function too. Notice at 3/2, the slope of the tangent line of function g was 9. And I can do that at all the points. And in this case, it's just linear. Right? So for each specific value, for each specific point, when I specify again x equals a, that gives me a point because g is in fact a function. I get a slope, I get a number out. And I can associate that number with a new function, right? Just as we did prior. So here's a link between these. Here's my function g. Now again, g was derived from f. Anyhow, g is just a function. When I specify a is 3/5, 3/2, 1.5, I get a slope. So again, g tells me the point, and there's a tangent line. It has a slope of 9, and that value defines a new function, right? 3/2, and the slope is 9, or the value is just 9. So g goes to this function h. And here it is in the picture. So the function g goes in, I apply the differential operator, and the function h comes out. Right? So here's my notation. G goes in, h comes out. Okay? That's what I have. All right, so again, let's look at it specifically. Let's put all the pieces together. I had my function f. My rule f of x goes in, I apply the differential operator, and fx comes out. In this specific case, the function was x cubed, and the function that came out was 3x squared. Again, how did we determine this? Well, we have the differentiation rules, but we came up with this from the definition of the derivative. Okay, so it constructs literally the slope of the tangent line. So again, the function x cubed goes in, the rule, then the rule 3x squared comes out, the function comes out by applying the differential operator. On the other hand, I can apply 3x squared in and get the function 6x. And when again, it's a rule, but I associate that rule with the whole function. 6x comes out. And I'm going to use the notation fxx, right? So notice f goes to fx, and the notation comes from the fact that it's ddx, right? So the variable is x, and I'm implying that I'm just piggybacking this notation. Well, again, if I just do it for the first derivative, I'm going to do it here. I'm going to apply fxx, right? So that's what I'm going to call the second function. So 3x squared goes in, 6x comes out. So fx goes to this function fx. And you can see this function 3x squared goes in, this function 6x comes out. And you can look at the whole connection. So you can see this function f connects to the function fx, which connects to the function fxx, okay? So there's this connection. Again, we'll see how this is useful. So what do we call this operator if we want to connect f to this fx? So here's the notation again. The function f goes in, and we call the function that comes out fx. Again, don't be hung up. It's just notation. You can call it f-tick. I don't really care. I think this notation is better, as again, you'll see when we do chain rule next. But f goes in, fx comes out. And again, it piggybacks the fact that it's ddx, right? This x is that x. So if fx goes in, then fx comes out. It's just consistent, right? So now let's look at it. Let's replace this fx by its definition. Right? I'm just going to replace this because I want to link f to fxx. So I'm just literally substituting in the definition, right? And then this is where the notation comes from, right? Just literally substituting in that definition. And you see, this doesn't mean anything. It's just notation. It's not a d squared over dx. What it really, it's just a piggyback of this, right? It looks like, it's not true. This is really composition of operative functions, the operator. But this is really dd, so it's d squared, and this would really be dx. So it's not dx squared. It really would be dx, the whole thing squared. But it just piggybacks from this notation. Again, it doesn't mean anything. There's no such thing as a d squared or a dx squared. This is just one chunk of a notation, right? Just one chunk of a notation. And it's a function or an operator, right? That's why I keep the big brackets here all the time. A function goes in, right? A value goes in, and a function or a value comes out, right? F goes in, I apply this operator, and fxx comes out as a function, right? And this is called the second derivative. The derivative of the derivative is the second derivative. And so this is the link. So the function fxx is, how do you compute it? Really, you compute it by taking the derivative of the first derivative, right? The first derivative is just a function. You compute it using either the definition or the differentiation rules, and we'll practice. Or what's its link to the connection to the function f via the second derivative. So this notation is the second derivative. Again, it doesn't break down into pieces. It's just one chunk. You could call it happy face, or I don't know, thumbs up emoji. This is just one chunk of a notation, right? And that's the connection. So if a function does have the second derivative, right, it means the derivative has a derivative, is what that says. And it's said to be twice differentiable, and we write d2, right? So this function is an element of the set of twice differentiable functions on this interval. And so forth and so on. I mean, there's nothing to stop you. You can take the derivative of the second derivative and get the third derivative. You can take the derivative of the third derivative and get the fourth derivative. And each of these gives you smoothness, right? We'll come back in a second, but here's the picture. The function f goes in, I apply the second derivative operator, and this function 6x comes out. Now again, you can't really directly do it. The second derivative is the derivative of the first derivative. The third derivative is the derivative of the second derivative. But just in terms of operators, this function f goes in and this function fx comes out. And this would be the notation. Now I was saying the smoothness. If a function is twice differentiable, we know a differentiable function, the function itself is continuous. So if the function is twice differentiable, then its derivative is differentiable, and in fact, the function itself is continuous. So twice differentiable is smoother than one differentiable. 3 times differentiable is smoother than 2 times. And again, this is a characteristic of the physical model. As I said, when I talk about the modeling the air in the room, for the conservation of mass, momentum, and energy, in fact, all you need is twice differentiable for the classical interpretation of that model. So the temperature distribution in the classical sense, and we'll talk about this the very last day of the semester, is twice differentiable. The temperature, density, pressure, all these quantities are twice differentiable. That's very smooth. It wouldn't allow things like shock waves and stuff, so that's the issue we'll address the last day of class. But okay, that's what it is classically. When everything is nice, that's what people were originally able to model with conservation, mass, momentum, and energy. So this smoothness is a characteristic of how you're modeling the air in that room. So the air in the room doesn't have a shock wave, so it is going to be twice differentiable. In fact, if you do the analysis and push that further, you can actually show that the air distribution has as many derivatives as you like. It's actually so smooth. There's nothing strange. It's actually any derivative you like, it has. So it's a very smooth, very classical distribution. And again, it is a characteristic between, again, physically it exists, but you're representing it as a mathematical model, and it is a characteristic in that mathematical model. Okay, so it is a modeling issue. So more derivatives means more smoothness. And I mean, you can continue to milk this. And when you have numerical methods classes, you'll see this. We had the optimization on closed and bounded intervals before. And again, we said if we only have continuity on the closed and bounded interval, I can tell you there is a max and min, but I can't tell you where they are. Now notice if I have continuity on the closed and bounded interval and differentiability on the interior, then I can tell you where it occurs. It occurs either at the endpoints of the interval or a zero of the function fx. Now again, if you're thinking about finding the zero of a function, what should you be thinking? What tool is in your toolbox? Again, flip through that. Flip through that. Don't get lazy. Don't get sloppy on that. Train yourself to think. You do not have infinitely many possibilities. You do not have infinitely many tools in your toolbox. Again, I've lost track, but what do we have? 4 or 5 of them? Zero tells me intermediate value theorem. So the intermediate value property, the function has to be continuous on the closed and bounded interval. If the endpoints have opposite signs, then there's a zero in between. So notice we need continuity, right? Need continuity. So if I'm talking about the function fx, I need the function fx to be continuous, right? Well, if the function fx is itself differentiable, then I know it's continuous, right? So throw in a little more regularity. Right? That's what this is saying. I'm kind of fudging the endpoints if you want to look at this carefully. I mean, you can get around it with things, but I'm just saying I am fudging the endpoints a little bit here. So if I basically say my function is twice differentiable in the interior and continuous on the closed and bounded interval, again, I'm kind of fudging this a little bit. I can use the intermediate value property to help us find the zeros. Again, in a numerical methods class, you'll see that this smoothness, these kind of issues play out. Now, I'm not testing you on this, so don't panic, but I'm saying this is how you use it, and this is why it really is important. When you're trying to come up with algorithms to solve actual problems, you'll see that this plays a role. Now, of course, one usually ignores it and just goes right to the algorithm, codes it to get done. But these are things that you need to consider. Why does the algorithm not work? You don't need the assumptions, and it's usually a smoothness issue. Okay, so this is just, I'm trying to give you a flavor of how we use this in practice. Now, this is the big thing, okay? It's a good question. What else can you do with this? I mean, that's right. Bingo, this is it. This is the big thing, right? This is one of the biggest things there is, Taylor series. And now, you can do this in Calc 1. Here we do it in Calc 2. I'm going to introduce a rule because I don't like the idea of just taking higher order derivatives as an exercise in pain and repetition. This is a big deal. Like I said, all the big topics you're going to do here, and you're going to use in engineering that come from calculus, or I'm going to introduce in this course. And Taylor series is a big, big, big deal. And you'll see it throughout everything we do. I'm basically saying, it looks kind of confusing, and we'll work out problems with this. I'm basically saying every smooth function, you need derivatives, looks like a polynomial. Okay, it's an infinite it's a polynomial with infinite terms, but okay, we'll talk about the approximation and everything later. But roughly speaking, every function looks like a polynomial. And you're going to see an example like this. So let's just plug and chug a simple one. Now, f of x equals sine x, right? And let's come up with a Taylor series based on at the point x equals 0. So again, there's x equals 0, and it's a function, so I know there's a y value. There's an ordered pair. All I have to do is take its derivative. So I have the function f. I take its derivative using the differentiation rules. The derivative of sine is cosine. How do I get the second derivative? I take the derivative of the first derivative. Cosine is minus sine, and so forth and so on. And I went up to 1, 2, 3, 4, 5 derivatives here. Okay, so it's here you go. I evaluate it at x equals 0, so when a is 0, right? And I just get numbers. And now here's my Taylor series formula. Don't be intimidated. It's pretty straightforward. You do a couple of problems and it's easy. You'll see it has a pattern. Notice with the first derivative, fx, it's over 1. With the second derivative, and notice the power here is 1. With the second derivative, it's 2 times 1. Notice the power is 2 for the second derivative. Third derivative, 3 times 2 times 1, power 3. Fourth derivative, 4 times 3 times 2 times 1, power 4, and so on. So it's actually pretty straightforward. I'm going to plug in my data point. A is 0, right? A is 0, A is 0, A is 0. Everywhere A is 0. I plug in f of 0 is 0. The derivative at 0 is 1, and so forth and so on. And notice, sine just looks like this. Now I can think about this. Sine is just this polynomial. Yeah, as you say, it goes on forever, but okay, let's just look at this practically. I mean, this is how it's useful. How do you define sine? I mean, analytically, you're going to say draw a unit circle, put a triangle in there, and take, what is it, opposite over hypotenuse? How is your calculator going to do that? How do you take the derivative of that? I mean, you can construct a function that way, true. You could construct all the points into it, but I don't know for a fact. How would you think your calculator is going to do that? Well, I'm just going to represent sine as a function. So you want to know what sine of pi over 6 is. Plug it in. Just plug it in. Here it is. If you want more accuracy, we've seen this over and over again. How accurate do you need it to be? How accurate is your calculator? How accurate are you storing data when you're doing calculations when you're coding? I mean, how many decimals is accurate enough? 8, 4, 16? How many do you need? So you take out as many terms as you need, and I just plug it in. Done. I take the derivative, plug it in, done. I can represent any function that has derivatives by a polynomial. If I want to differentiate it, turn it into a polynomial. I want to integrate it, turn it into a polynomial. You say, well, I'm losing accuracy. How many decimals is enough for you? This is how you need to think. And well, we're going to explore this idea. But this is a big deal. Turn it into a polynomial. That's how I see things. Okay? So again, notice, if I only go to one term, it's called the first tangent polynomial. It's actually it's a linear approximation. So if I only go up to the first derivative, it's the first Taylor polynomial. If I go up and include up to the third derivative, it's the third Taylor polynomial, and so forth and so on. So again, do I make this should actually stop at the fifth term. There's a typo there. It should just stop at x5. So again, will I lose some accuracy? Yeah, but again, how accurate do you want to be? And again, we'll see this. Here's a picture. I mean, you can see for yourself. So the red line is the sine function, the graph of the sine, right? Notice, the first one, the blue, is the first Taylor polynomial, which is the linear approximation. So again, I'm based at 0, 0, and it's pretty accurate. Again, how accurate do you want to be? So let's say you go between minus a half, and this block here, minus a half plus a half, and minus a half plus a half on this box right here. I mean, you can see there's a little bit of error at the ends. But again, if I want more accuracy, I have two choices. If I want more accuracy, I could take a smaller neighborhood. So instead of going from minus 5 to minus a half to plus a half, go to minus a quarter to a plus a quarter. You can't see much of a difference, right? If I want more accuracy, go to 1/10, minus 1/10 to plus 1/10. Okay, so that's one approach. But another approach, again, if I have more smoothness, if I can take more derivatives, and this is a key to how all this stuff plays out, right? This is a key how all this stuff plays out. If I have more smoothness, I'll take, say, the third one. So the third one is this kind of gold line. And notice, on minus a half to half, you can look, zoom in, it's more accurate. It's more accurate on a given neighborhood. Or if I like to accept a certain error, notice I might be able to take a larger neighborhood. I can go maybe from minus 1 all the way to 1 and have the same accuracy as with the linear approximation on this smaller neighborhood, minus half to half. This gives me options, how I approach the problem. If I have more smoothness, I have the possibility of considering a higher order approximation. right? A third order Taylor polynomial. And if I go to the fifth Taylor polynomial, again, how accurate do you want to be? The fifth one is pretty accurate to what? Maybe minus 3/2 to plus 3/2. I mean, it's pretty good. So again, think about if you're going to program this on the calculator, or if you're going to take the derivative of this or integrate this. Turn it to a polynomial. Turn everything, think of every function that's defined in smooth as basically being a polynomial. Do you lose accuracy? I mean, get over it. How much do you need? Right? That's the idea. This is how we actually use this stuff. But Taylor approximations require smoothness. Okay? So I'm just saying, I can, if I fix the neighborhood, the higher, so fix the neighborhood, look at the picture, the higher the Taylor approximation, the more accurate it gets. That's what I'm saying. So if I want to fix the neighborhood, right, go minus half to positive 1/2, minus a half, positive 1/2 here, right? A fifth order Taylor polynomial is going to be more accurate in general than a first order Taylor polynomial on this fixed neighborhood. Okay? Or if I want a fixed accuracy, I can take a bigger neighborhood. So if I want a fixed accuracy, specify whatever your error is, I can take a larger neighborhood and associate a larger neighborhood with a higher order Taylor polynomial, right, and get the same accuracy. I mean, this is a big deal. I mean, this is a big deal. This is a very big deal. Like I said, in differential calculus, I'd say the global optimization on closed and bounded intervals and Taylor approximations are by far the big results. By far the big results. Okay? So again, your neighborhood has to be small enough. You have to be smooth enough, and so forth. Here's an application. Here's a problem. Now, again, to me, this is what I see. Sine x is a Taylor polynomial. Okay, this is an application. This is how it gets used. Right? This is the big deal. Sine x to me is just this polynomial. This polynomial. Now, you're going to make this stuff. We're going to do it in a lab, and you're going to make all this precise next semester in Calc 2. But this is the idea. Sine x, I look at it, I mean, I just see a polynomial. So sine x over x is just this polynomial. Now, it's not defined at 0, but let's look at it. I have to do an extension, and I'm being sloppy with the notation, but I'm just trying to emphasize the point. Sine x over x to me is just a polynomial. Again, you have to take precautions. We'll be more careful in the lab, and so forth and so on. But sine x over x is just this. And I can evaluate this. Really, I need extension theorem, but 1. Just again, define your extension, plug in. Again, this notation is sloppy. I've talked about it when we did limits. 1. It's that simple. You can go on the web, just type in Taylor series calculator, and you can generate Taylor series for all your functions. It takes the derivatives for you. It works it all out. Again, I'm not particularly interested in derivatives. I am interested in Taylor series. Okay, and this is why I care. It makes the kinds of calculations we do straightforward. Again, you think calculus is all about these algebraic gimmicks, knowing all these tricks, being punished into memorizing tons and tons of formulas. It's not. This is calculus. I mean, again, you make all this precise and you'll talk about it in Calc 2, but the idea of the Taylor series is going to preeminate so many things we do, and that's why throughout this whole course, that's why I introduced the idea, and we're going to see it. Now, I'm not a fan of L'Hopital's rule. I mean, you're welcome. You should learn it because people like to throw L'Hopital's rule at you. I think because it's fun to say L'Hopital, everybody loves to say L'Hopital. There's L'Hopital this. You go to a party, I say L'Hopital. Oh, she's so smart, L'Hopital. I don't know. You could do Taylor series, but you're expected to know it. In the particular case, if you take the limit of the function at 0, the function g is 0. If you want to evaluate the limit of f over g, you can evaluate the limit of the derivatives and so forth and so on. You can read it as well as I can. Here's an example of it. You just plug in, it works fine, whatever. I mean, in the lab, we're going to explore how you do these problems with L'Hopital and how you do these same problems if you did Taylor series. I don't think the Taylor series is harder, and it's more general. So for me, That's my opinion. If you love to say l'orbital, knock yourself out. Okay? All right, again, we're going to explore these concepts more in the problems and really all through the next sections and so forth and so on. This is going to permeate the entire course, and it's a big aspect of calculus. So again, keep this in mind. Functions look like polynomials if they're smooth. That is a big deal. That global optimization theorem on closed and bounded intervals, those are the two big ideas. To a lesser extent, what do we have? Intermediate value property. Sign intermediate value property. It tells you where something is positive and negative. So these are really your tools, right? Don't get hung up in the fact that everything is the derivative of gimmicks and tricks. This is how we use it. Okay, good luck. We'll explore more ideas later.